Yes. No, I couldn't do that with the gauge transformation. In particular, I can't change the magnitude of the scalar field. Well, I know that the Goldstone bosons correspond to precisely those modes generated from phi infinitesimally. These are the modes that generate the Goldstone bosons. Okay, infinitesimal rotations about the minimum. Okay, they are in fact generated by group transformations. Therefore, by applying a gauge transformation that counteracts that very self-same group transformation, I can put this equal to 0. You want a general? I can also give you a general proof for any compact group, if you wish, if you have mathematical background. There is. Well, it's first published in a paper by Weinberg. There's an acknowledgement in the paper. That's okay. That's okay, and it's a proof. It's a proof any idiot could have thought up, and this idiot happened to be the one that. No, there is a general argument which breaks down if phi has a 0, of course. If you are imagining classical field configurations very far from the configuration of minimum energy, so that phi equals 0, then it's then the gauge condition it becomes troublesome. It doesn't tell you which way to gauge transform. That doesn't bother us, of course, when we're doing perturbation theory and tree approximation, because then we're always considering, we're expanding about the configuration of minimum energy. The deviations from that configuration are small. I mean, quote, Weinberg's proof, unquote, is valid whenever tells you can always gauge this way, but it doesn't tell you the gauge is uniquely determined. And it's not when phi has a 0. But in fact, as I say, to say you can always choose a gauge such that the Goldstone modes are gauged away is evident from the way we have found the Goldstone modes. They are precisely those modes, that surface hypersurface within phi space that is swept out by the action of the group generators on the ground state. And since it is made by group generators, it can be unmade by group generators, and that's just what a gauge transformation does for you. Other questions? Okay. We're now going to turn, after having investigated gauge field theory, we've investigated gauge field theories as classical field theories, and we've investigated the spontaneous effects of spontaneous symmetry breakdown in gauge field theories as classical field theories. From our previous experience with theories of scalars and spinors, we know that if we can construct a quantum theory, this old derivation could be reinterpreted as the first term, the tree approximation, in a systematic quantum expansion by the same methods as before. However, we have to construct a quantum theory of gauge field theories. In particular, if we ever want to compute higher order corrections to the tree approximation, we have to compute that. So I will now turn to the problem of quantization. Of gauge field theories. We have, of course, already quantized earlier this semester one gauge field theory, the simplest one. It may have seemed complicated when we were struggling through it, but it's simple compared to the objects we have to confront now, and that is electromagnetism. And there we found a magic method, which was the Faddeev-Popov method. And I will use that here. Let me refresh your memory of how Faddeev-Popov quantization worked in an ordinary gauge in electromagnetism. I will leave little blank spaces on the board where I will later put in indices to turn the formula into a formula for a non-abelian gauge field theory. We consider all of our dynamical variables, scalar, spinor, vector fields, whatever, under a single name, phi. And our first step was to choose a gauge. That is to say, to choose an equation f of phi equals 0 that fixed the gauge. We had several choices. Two that seemed especially useful were axial gauge This was a useful gauge because we could prove directly that the Faddeev-Popov prescription was equivalent to canonical quantization in that gauge. That was the method I used. The other gauge, which we found useful because it gave us simple Feynman rules, were the gauge conditions d mu a mu equals some function of x minus
33, Dick.
0. Thereby subsequent integration over the function f, we were able to put the d mu a mu up into an exponential and get Landau gauge, Feynman gauge, etc., the so-called covariant gauges. Once we've picked a gauge, Faddeev-Popov says z, the generating functional, is some normalization factor, functional integral over all the fields, either the original gauge invariant action, a functional delta function of f of phi, times a determinant delta. Delta was df d omega. Of course, since it's multiplied by a delta function, we need only evaluate it at the point f equals 0, where omega was the original gauge transformation. The Faddeev-Popov ansatz had the great advantage that although just writing it down, of course, does not tell one that it is the right thing to do for the theory, it does manifestly give an expression that is gauge invariant, independent of the choice of the function f, as long as f is a well-posed gauge, as long as it fixes the gauge. And therefore, if we could prove it was valid in one gauge, and in particular we proved it was valid in axial gauge, we then knew it was valid in all other gauges. Okay. This is an aide-memoire. If you didn't go to the previous lecture, the first half hour or 45 minutes of this lecture will be completely incomprehensible to you. But if you did go, and there's some little point that has slipped your mind at this stage, let me know. Now, to generalize this to a field theory in which there is a large gauge group, instead of just gauging a U1 group, we gauge a U3 group or a U2 group or something like that with many gauge parameters, is essentially trivial. We have many gauge functions, so we need to impose many gauge conditions. Therefore, we will need one gauge condition for each group generator. A typical gauge condition might be this, or this. Of course, we've got to integrate over the surface where all the gauge conditions are held fixed. So we have a delta function for each gauge condition, And finally, the determinant. Whoops, I wrote D. I'm sorry, that should have been determinant. Someone should have caught me. It's, of course, a functional determinant you need to cancel out the delta function, the Jacobian factors arising from integrating the delta function. The determinant will be a determinant of this kind, not only a determinant in function space, but a determinant in AB space. Manifestly, by trivial extensions of the argument as given as before, this generalized Faddeev-Popov ansatz with n gauge conditions instead of just one is independent of the choice of gauge. Don't have to do that all over again. The next question is, firstly, can we prove it as equivalent to canonical quantization along the same lines as before? And secondly, what does it look like in a gauge of this kind, which we know is a gauge that gives us nice Feynman rules? So the first step I will take will be to show it is equivalent to canonical quantization. This step will be really incomprehensible to those who did not understand the previous version, because I will not go through the whole argument again. I will just point out the possible points where there might be differences and show that everything goes through okay and is unaltered. So the first choice of gauge, so go to sleep if you didn't understand that before, and after 5 or 10 minutes I'll wake you up again and we'll do something you can't understand. Great. Here we go. To axial gauge. The change in the delta A3A equals CABC delta omega B delta, A3C minus, remember we've rescaled our field, so we've got G inverses and G's floating around, minus G inverse d mu delta omega A. D3, thank you. Now, this is a mess, but fortunately, since we only have to evaluate the determinant at the delta 0 of the delta function, the first term is in fact 0. Therefore, it's just the same as in the previous case. Delta is the determinant of delta AB, because there's an A here and an A here. G inverse D3 with a minus sign if you're a purist. But anyway, that does not depend on any of the dynamical variables in the theory. It is a constant. So you can just absorb it in N without worrying about it. Thus, delta is irrelevant. Now, as you recall, the next step, as you probably don't recall, but as I recall, the next step in showing that the axial gauge thing was equivalent to a canonical quantization was to write the theory in so-called first-order form, where you treated the F's and the A's as independent variables. That trick, of course, because that's the only part that's relevant. I may have all my coefficients wrong in sign. I did this in some haste.
Read me, John.
Minus 1/2. No, that's going to come out right. F mu nu A. D nu A mu A minus D mu A nu A plus CABC A nu B A mu C and a G here. This is plus dot 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 for the other fields in the theory. That's not going to change much. That's just going to be normal electrodynamic type couplings, just a bunch of them, so I'm not going to worry about that. It's these possible nonlinear terms that may give us trouble. If you treat f mu nu a as an independent variable and vary it, you obtain the equation of definition for f mu nu a. F mu nu a equals this monstrous expression in parentheses. And then you plug that back into the Lagrangian, and you obtain our original second-order form of the Lagrangian, minus 1/4 f mu nu squared. Now, as you recall, the thing we did was to show that this was equivalent to canonical quantization by dividing the variables, in the abelian case, up into 3 sets. First, well, of course, we're still working in this gauge, A3A equals 0. There were AI in the abelian case, AI, which were like coordinates. F0I, here I is only 1 and 2, there is no A3. F0I, which were like momenta. Those were, in fact, the only independent variables. And then there were, continuing this table on the other board, there was everything else. A0, Fij, Fi3, and F03, which were constrained variables, superfluous variables that were given in terms of the coordinates and momenta at a fixed time by solving the differential equations, by the Euler-Lagrange equations. Constrained in the sense of the Hamiltonian problem, given in terms not independent initial value data. Okay. Then our argument went, we just zipped through the functional integral. Because the constrained variables entered at most quadratically, and the coefficient of the quadratic term was a constant, was a set of constants independent of the fields, we just integrate over the constrained variables and eliminate them. The Hamiltonian form of the functional integral, which we know is equivalent to quantization. If you don't remember that, as I say, go to sleep, but that's how we did it. So the only thing we have to check here is to do exactly the same thing. Put a little index A on everything, and check that the constrained variables enter the Lagrangian at most quadratically, and that the coefficient of the quadratic term is a constant. We obviously only have to worry about the extra trilinear term. So let's go through them one at a time and see what happens. A0A. Well, that can enter here once, all right. But then this thing will have, since this is an antisymmetric tensor, will have to be a space index. This, therefore, I. So if this is 0, this is I, which means this is 0I, which is the momentum. Therefore, that particular term is just linear in the constrained variables. So that's no problem. It's a momentum times a coordinate times A0I. No problem. That's a linear term. Next, Fij. Well, that can enter here, of course, but only if one of these is I and one of these is j, in which case those are two coordinates. So that's also linear. And that's okay. Next, Fi3. Well, if this is I and this is 3, we don't have the extra term, because when this is 3, this vanishes by the gauge condition. So there's no term to worry about. So that's trivially okay. And the same thing goes for F03. There again, the term proportional to G does not enter. So the machine runs. It's the same machine, and therefore I didn't want to go through the proof step by step. I just wanted to point out that the extra terms have absolutely, that distinguish the non-abelian case from the abelian case, have absolutely no effect on the argument. Thus, the Fadi of Popov-Ansatz is okay. It is equivalent to canonical quantization by exactly the same proof we gave in the other case. And those of you who went to sleep can now wake up. Wake up, because we're now going to do stuff that does not depend on previous knowledge. We're going to explore the consequences of the ansatz in one of these Landau-like gauge, not Landau, Lorentz-like gauges where d mu a is Fa. Are there any questions on the thing I went through? It's dull, but it had to be done to keep us honest. Yeah. Now, next stage. Of course, axial gauge is wonderful for proving the theory is canonically quantizable, but terrible for deriving Feynman rules. It's not even covariant. So we'll have to, we know what's a nice gauge. It's this one, where this is an arbitrary function of x. Now we have to compute the change in this object. Alpha, d mu a mu, a. Fa is just a C-number function, doesn't change under a gauge transformation, equals, bring the derivative outside. Boy, I wrote it in a messy way. Well, I'll just work it out afresh. C A B C delta omega B A mu C minus G inverse thus, variation of d mu a mu a over omega b. I'll factor out, for reasons that will become clear later, a factor of G inverse. That's not going to bother me. That's just going to make a determinant. I'll keep the d mu outside. And I have from this term here, the differential back up to the minus. Differential operator. Plus AB. That is that differential operator. Of course, the variation of one thing with respect to another is an operator, something that turns a function of x into a function of y. The other term I write as plus minus DABC. A mu C, and I've got to put a G in front to take care of my G inverse. Now this combination can be written in a somewhat nicer form by exchanging the indices B and C and turning the minus sign into a plus sign, because there you see the thing we have here is exactly the covariant derivative operator acting on a field that transforms according to the adjoint representation of the group. So delta equals constant times the determinant of minus d mu acting on a set of fields that transform according to the adjoint representation of the group, i.e. like the gauge fields themselves, or like the field strength tensors, I should say. Well, it's trivial to write that determinant in terms of ghost fields using our ancient trick, because if we had introduced a set of ghost fields, then this is equals constant, which we're not concerned about since it is absorbed in the normalization factor. A set of ghost fields, one for each group generator, product on A, e to the I, S ghost, where S ghost equals a very simple thing, d mu eta bar A, covariant derivative of eta A. We always know how to write determinants as integrals over ghosts, and here we have to do it because this thing is not a constant. It does have this non-zero term in it. Is everyone happy? That's our famous trick, which we exploited in studying derivative couplings, where we write a determinant in terms of ghosts. This is the only difference between the quantization of the abelian, the derivation of the Feynman rules for the abelian and the non-abelian gauge field theories. In the abelian case, the structure constant was 0, and therefore we had simply a determinant of a constant, and we didn't have to introduce any ghost fields. We could have if we were super purists, but it would have been ludicrous to do so. Here the determinant does depend on the dynamical variables A mu A, so we have to introduce ghost fields. The rest of the argument follows as before. We can exponentiate the delta function by integrating with an appropriate function of f to turn it into a d mu a mu squared in the exponential, and we arrive at the following Lagrangian. Effective Lagrangian, that thing which has to be put into the functional integral, the Feynmanian, not the Lagrangian. Original gauge invariant Lagrangian plus a free parameter alpha. Could be different for different fields, but nobody bothers to do that. D mu a squared to adjust the transverse part of the propagator as we please, plus the ghost part, d mu eta bar A, d mu eta A. Notice the ghosts now have real dynamics. In tree approximation, they are massless, charged, both fields. Massless because there's no mass term here, interacting trilinearly with the vector meson. They have a very funny looking interaction. It doesn't look gauge invariant. Of course it doesn't look gauge invariant. The whole point of the Faddeev-Popov ansatz is to pick a gauge which destroys gauge invariance. This doesn't look gauge invariant either. It's not gauge invariant. They're just to be treated like normal particles, except that, strangely enough, they have a Fermi minus sign for every closed loop. That's the peculiar feature, but that's what makes them ghosts. Okay. Well, are there any questions? Any questions? Of course, I mean, the whole thing has got to work out. You'll never get a negative residue in a Green's function from a ghost loop going around, because a negative discontinuity, because every gauge invariant quantity could as well be computed in axial gauge where there are no ghosts. So the ghosts always have to cancel off against longitudinal photons or what have you in any specific calculation of the gauge invariant quantity. But they're there. You can't get away from them. It was a great discovery that they were necessary. In fact, the history is interesting. Feynman and Bryce DeWitt independently, well, Feynman and DeWitt at around the same time started trying to quantize gravity by guesswork, and that was a messy problem. And then they realized that Yang-Mills fields had many of the same features as gravity. Remember my earlier discussion as to why a nonlinear self-coupling of the fields is necessary. So they said, well, by God, that's simpler than gravity. At least we only have to go up to quartic terms instead of an infinite series, so we'll try and quantize Yang-Mills fields. Independently, they did the same thing. They tried to guess the right Feynman rules and guessed them and then computed away and discovered that they didn't work. They got a breakdown of unitarity and a breakdown of gauge invariance and everything else, and realized that the missing term could be compensated for by a ghost on the one loop level, and then gave up because they didn't know how to go beyond the one loop level. And there the matter sat for, I would guess 8 or 9 years until Faddeev and Popov came along and invented this method and showed that the ghosts not only cured the problems on the one loop level, they cured the problems on all levels. The propagators weren't equal to total cross sections, even scattering amplitudes. They got extra pieces that are canceled if they look at Yang-Mills meson scattering without the ghosts. then in the one-loop level, the imaginary part of the forward scattering amplitude was not given by the optical theorem. The reason it wasn't is that there's an extra minus term, which they had left out the first run-through, which consists of a box with a ghost going around the box. Now, this Lagrangian is truly horrendous, and we are not going to do any non-tree level computations except for one fairly trivial one in this theory. One can, of course, in principle, read off the Feynman rules just by standard methods. Every derivative becomes a momentum, etc. But they become rather horrible because everything is carrying so many indices, especially if you look at multi-vector meson vertices. Everyone is carrying a momentum, a Lorentz index, and an internal symmetry index. So things get god-awful looking. I'll write down a few simple things and work out one complicated one. I won't even try and write out the complete set of Feynman rules because everyone would get bored and no one would remember them. For pure gauge theories, there is the gauge meson, which carries an index mu and nu, and index, well, I should put mu on the initial one, I guess, A, nu B. And that has a propagator that is minus I. That's just the conventional one. The mesons are independent. Minus I delta AB. G mu nu minus K mu K nu over K squared over K squared plus I epsilon. They always have mass 0. And plus alpha K mu K nu over K squared plus I epsilon. The usual form for abelian theories. Perhaps I wrote minus alpha the time before. I didn't bother to work it out afresh to see whether it's alpha or minus alpha, but that's unchanged. And then we have the ghosts, which are charged particles. Eta is not equal to eta bar, so we indicate them by a directed line. They have an A and a B, and their propagator is simply plus I, this conventional propagator for a massless scalar field. The only unconventional thing comes when one considers ghost loops, and then one has to add an extra minus sign. And then there are all sorts of interactions. There is, in particular, coming from here, a trilinear interaction from this term. Where did I write it down? I erased it. Remember what F mu nu is. It's a term linear in the derivatives of the fields plus a term quadratic in the fields. So from the cross term, there'll be an interaction like this, which I will shortly compute because that's the messiest one. It's got derivatives and internal indices and space-time indices. It's absolutely horrible. There is a term of this kind, which comes from the square of the non-derivative term, and that's actually not quite so horrendous because it doesn't at least it doesn't have any factors of momentum in it to keep straight. And then there is an interaction, of course, of the gauge fields with the ghosts coming from the A mu factor hiding in the covariant derivative of the ghost fields. All four of these things are horrible to work out, and I'll just work out the first of them, which is the most horrible of the lot, and make some remarks about its physical meaning, because people normally see it and scream when they see it in a paper. They say, oh, where does that come from? And I'll try and show you that it's really very physically sensible. The term in the Lagrangian that's going to do the dirty work, it says minus 1/4 originally, but I'm taking one from each side, so that turns into minus 1/2. D mu A nu A minus D nu A mu A C A B C A nu B A mu C. We can simplify this a little bit in first instance by observing that this is automatically an antisymmetric tensor in mu and nu, so there's no need to keep both terms here one of them gives the same thing on the summation as the other. So this is simply minus 1. And I think I now changed the names of my indices because I wanted to use mu and nu for another purpose. This is a computation which I will never get straight. Yes, d alpha, a beta a, c a b c, a b alpha, a c beta. Now, we want to consider the vertex, which I had written down there as small. I'll now write it big because I want to label everything. Here I have a vector meson carrying index A, mu, momentum P, B, nu, momentum Q, C. No. I have reasons. You'll see. Otherwise, you'll get terribly confused. C lambda r. I labeled these alpha and beta because I want to say, well, there's the possibility alpha is mu, and and if I called them all mu and nu, everyone would go crazy. These momenta are, of course, not independent, but it's useful. P plus Q plus R equals 0, and I'll choose them all directed inward. Now, this thing is horrendous to figure out what this vertex is simply because there are so many possibilities is which field absorbs which of the three mesons. We've got to worry about all of them. There are, in fact, 3 factorial or 6 possibilities coming up. Okay. Some factors are common. Well, certainly there's a G in here, which I carefully forgot. Some factors are common. It'd be a dumb theory if the interaction didn't have a coupling constant in it. There's a minus IG coming out, and because we're always differentiating an incoming momentum, we'll get a minus I from that. That's like an annihilation operator. Now, there'll always be a CABC in some permutation or another, and aside from minus signs, one permutation is the same as another because of our cunning trace norm orthogonality condition. So we can just write that as CABC and worry about whether we get plus or minus signs in various combinations. Now comes the mess. Let's take the case where this meson is absorbed by the first factor, that carrying the A, and the other mesons are absorbed by the B and C. No permutations, just as stated. Now, the first meson is being differentiated, so we get a P, because the first meson carries momentum P. P with what index? The same index as the derivative, which is the index of the second meson. So it's P nu. The other 2 indices are being summed together, so I get G mu lambda. Okay, is that clear? Now, there are 3 other terms that are trivially obtained from these by cyclic permutations, of which one I put on which one. 2 other terms, I should say. And those I can just cycle around. Here it's P nu, G mu lambda. So I cycle around. I get Q. The next one over is lambda. Okay. Then I've got the remaining 2 indices to sum, G mu nu. Then I've got R, the next one over is mu, times G nu lambda. Then there are the terms where I go anticyclic. That means instead of summing each of these with the index, attaching to each of these momentum the clockwise index, I attach the anti-clockwise index. C therefore changes sign. So I have P lambda, G mu nu, minus Q with the next one up, Q mu, G nu lambda, minus, God, what a mess, R nu, G mu lambda. Okay, but if you keep your wits about you, you can derive it. God have mercy on he who tries to do a 2-loop computation with these things appearing at every vertex and having to be summed over. That's why Tini Veltman invented a computer program for doing computations in Yang-Mills theory, just to do the index sums. It's good.
Like, say, the box diagram, would that in each.
Yeah, well, that's not so hard, actually. I'll actually do a one-loop calculation shortly, but of the effective potential, which is pretty simple. Very simple object. There, by being cunning in our choice of gauge, we can make the indices take care of themselves. So this is it, and obviously similar calisthenics, although slightly less strenuous, will give you the other two kinds of fundamental vertices, but I won't bother to derive them. What I would like to explain to you, though, is that this vertex, in fact, has a very simple meaning. Suppose we consider the theory of an ordinary photon coupled to scalar charged mesons. I'll label the momentum in the same way, all going inward. So that's P, Q, R. This carries an index mu, and these are scalars that have nothing. Now we remember from scalar electrodynamics what that vertex looks like. That vertex was proportional to the sum of the incoming and outgoing momentum, but one is incoming and one is outgoing. So it's Q mu minus R mu. Okay? Now, we've got a term just like that. If we look at the G mu lambda term here, that has got, whoops, sorry, wrong term, I want the mu's, the G nu lambda term here, that is in fact Q mu minus R mu, or as I've written it, R mu minus Q mu. So this term can be read, this term and this term, as saying this one acts as a photon, and these act as spinless charged particles. It has a coefficient, which of course is given by the group Clebsch-Gordan coefficients. Okay? And it doesn't matter what polarization state they're in, what mu or nu is, so there's just a G mu nu. G lambda nu. G lambda nu, G lambda nu. Each of the four gauge mesons, here and here, just act like four independent charged scalars. But of course, we can look at it any which way. We can say this is like a photon and this is like a charged particle. Or we could say this is like a photon and this is like a charged particle. Or we could say the third one is like a photon and those other two are like charged particles. That's the wonder of Yang-Mills theory. In the case of SU2, the 1 and 2 mesons act as charged particles when seen by the 3, which acts like a photon. They're the source of the 3. But the 2 is also the source, sorry, the 1 and 3 are the source of the 2, and the 2 and 3 are the source, you know. It's amazing, amusing but confusing. So you just have the sum of this thing over 3 permutations, depending on which one you think of as the photon. In the same way as an exercise for you, I'll leave it to you to work out, if you're curious, the 4-photon coupling, the 4-gauge meson coupling, which also is a mess of permutations, and show that that can be thought of as just summing over permutations of this thing, which is also there in scalar electrodynamics, changing which pair you think of as the pair of photons and which pair you think of as the pair of charged particles. So really it's not more complicated, although it looks more complicated, and certainly the computations are more horrendous. It's no more complicated, in fact, in a structure than the ordinary electrodynamics of charged scalar mesons. It's just that you have many options of which of the mesons you're to think of as the photon, and therefore you have sums over many permutations. Okay, that's something you won't find in the papers, but I think it helps understand why these complicated structures necessarily arise in a physical way, semi-physical way at least. Any questions? Equal to 4. All of our propagators go like 1 over k squared. We have either 4 undifferentiated fields at every vertex or 3 fields, one of which is differentiated. So we have the first half immediately of a proof of renormalization. The only counter terms we will need will be counter terms of monomials of the same form as monomials appearing in the original Lagrangian, with no more fields and no more derivatives. We do not have the second part of the proof of renormalization, which is to show that these monomials come through with exactly the right coefficients to correspond to a redefinition of the parameters in the original Lagrangian. That is to say, the connection between the various counterterms, which we obtained in electrodynamics by a lengthy argument systematically exploiting gauge invariance and, as a consequence, the ward identities. That argument does not go through in this case. The reason is that argument is it depends on the term that breaks gauge invariance in the Lagrangian being no more than quadratic in the fields. That's true for the alpha term, but it is not true for the ghost term, which is trilinear in the fields. Therefore, another proof is required. The original proofs were unbelievably horrible, and were gradually improved and simplified until finally Stora and two friends at Marseille. Does anyone here who knows? John? Becky, Ruel, and Stora. Found a proof that was only believably horrible. I was going to give it to you when I thought about teaching this material, but it would take around 40 minutes, and I don't want to spend the time, so I refer you to those papers if you want to see the proof. Take my word for it. It is possible to prove that Yang-Mills theory is strictly renormalizable. Okay. I'm sorry. I feel I've made myself a dishonest man. The symmetry breakdown is irrelevant. That we've already established, because you can compute the generating functional without asking whether or not there is symmetry breakdown or not, and then go and look at the generating functional and see if you have to shift the scalar fields. So if you have proved it as renormalizable, you've proved it as renormalizable, regardless of whether symmetry breakdown occurs or not. That comes from the same argument we gave for our scalar field theories. Okay. It doesn't matter. Well, it may matter in if you're really giving a proof on a fine technical level. For example, you may worry about if you do your subtractions LBPH, and if you don't have symmetry breakdown, you have all those massless vector mesons, which may give you hideous infrared divergences that make things blow up at the BPH points. Okay, but on the level in which we're working, it doesn't matter. You wonder if you prove Hepp's theorem. Have you proved Hepp's theorem with the subtractions at a Euclidean point, for example? Things like that. But in principle, because we have the generating functional formalism, the question of renormalizability and the question of the occurrence of spontaneous symmetry breakdown are completely separated. First you renormalize, then you look at the renormalized theory to see if symmetry breaks down. I should also say that in certain cases, just as a footnote to my apology for not giving the proof, in certain cases, the naive ward identity, especially cases involving mesons coupling to gamma-5 type currents, axial vector currents, the naive proof of the ward identities without great care taken with the cutoff can break down. This is called the occurrence of anomalies. And you sometimes have to worry. There is a set of rules. These anomalies have been cataloged. This exercise in osanomy, in the categorization of diseases. And you have to check that they cancel among the various axial vector currents. And this is another long song and dance, which if this course was running on for 3 weeks, I would be delighted to step through for you, but which I cannot, do not have time to do so. No, the Feynman rules weren't even known.
So I was using the method. That's what related to this stuff.
No, it was not known. It was conjectured. But nobody even knew the Feynman rules. You couldn't prove renormalizability until you knew the Feynman rules. How can you tell the divergences cancel from all the graphs until you know what the graphs are? Vadev-Popov was when, 68, thereabouts? 67, 68. Well, it gets pretty complicated. I mean, you've got to look at it the right way to make it look simple. Okay? Otherwise, you go calculate to a certain level, and then you vomit up a bunch of indices and decide to look at another problem. It's just organizing it. Okay, Vadev-Popov found this neat way using the functional integral to organize it, so you could see it all happening in one fell swoop without going crazy, writing down things like this and computing it. Veltman was probably the only one who was really working hard on Yang-Mills theory throughout that period. And he in fact, being a very man with great good taste and realizing, he says, I'm not a super analytical genius. If I'm going to tackle this problem, I'm going to have to learn how to manipulate all those indices. So he invented this computer program, Shunchip, to manipulate the indices for him. But he had made an error. He said, well, obviously, the massless theory is the limit of the massive theory, and the massive theory I know how to quantize. Okay, so I'll just go ahead with the mass. There's no gauge invariance there. He just put in a mass term. He said, I'll just compute everything and then let the mass go to 0. And unfortunately, for Yang-Mills theory, unlike electrodynamics, the massless theory is not the smooth limit of the massive theory. I can't, that's a well-known result. Again, as we approach the last week and a half of the course, I will have to say there are things I will not have time to prove to you, and that's one of them. But in fact, the mass zero theory is not the limit of the massive theory. It doesn't work out like it does in electrodynamics. You can get rid of one line. You have these, if you have a SU2 theory, you have 3 photons coming together at a vertex. You work things out, you can always get rid of one of the 3 longitudinal photons, but you can't get rid of all 3 of them simultaneously. And helicity 0, I should say. And there is just no way of making it run. So he was unknown to himself and unknown to everyone else pursuing a dead end. That's a rough memory of the history. I may have scanted credit for some people. The Faddeev-Popov paper was widely not understood when it appeared. It was obscurely written. It took around a year or 2 for it to sink in. In fact, it took Ed Hof's independent discovery of the renormalizability. They did it in an extremely strange way. But then it finally came together. Garbage. That starts out with the massive theory and plays around with it. That was invented by Yang and Lee. It was a good attempt. Didn't work. It turned out to be garbage. That wasn't clear at the time. Yes? They weren't reading other people's papers, which was a good thing because they did very good physics. He essentially independently found the right Feynman rules, and he discovered a point I will come to in a moment, which is that the whole point of spontaneous symmetry breakdown is that it enables you to construct a theory involving massive vector mesons, which might simulate, in the way I will describe in the latter half of this lecture, weak interaction theory that is renormalizable. I will come to that. Ed Hof made that discovery. And he didn't know that Weinberg had proposed a similar model, but was unable to see any reason why it should be renormalizable 2 years before. Okay. That's an easier question to answer after I reconstruct the things in unhistorical order, and then I can tell you what part was discovered at what time by what person. Okay, but now I'm not doing it in chronological order, so half the story is missing, so it's hard to answer historical questions. To make it really work, at Hof's original papers, it was just a formal argument manipulating infinite quantities and imposing gauge invariance when necessary. I remember it very well. Tini Veltman I met in Marseille, and he said, a graduate student of mine has a renormalizable theory of charged vector mesons. They weren't even thinking massive charged vector mesons. And I said, I don't believe it. And he said, it's true. And we were almost about to make a bet, but then which is a good thing we didn't, because I would have lost a lot of money. And that's why I'm one of the few people in the world who doesn't mispronounce Ed Hof's name, because he said his name is Gerard Ed Hoft. I said, okay, and then I saw how he got the preprint and saw how he spelled his name, and I said, what a funny way to spell Ed Hoft. Instead of saying the reaction of everyone else, which is what a funny way to pronounce Thuft. So anyway, now I want to do one computation in this, wasting a lot of time. Well, that's all right. That's that reading period. Reading periods for wasting time. One computation in the general theory, and that's the computation I've been doing all along, the computation of the effective potential, which is a very simple object because it only involves external scalar lines, and that all carries zero momentum transfer. So even though you're summing up a huge number of graphs, they're summing up a huge number of very simple graphs. Let me refresh your memory about what we've got so far. We have a general theory, which we now generalize even more to involve gauge fields as well as scalar interactions and Fermi interactions. The effective potential, V, which depends upon the classical scalar fields, is going to be a sum of a bunch of terms. There'll be the zeroth order term. There will be the contribution from the scalars themselves, which we computed 2 lectures ago. The contribution from the fermions, which we computed. As I will show, the computation from the gauge fields, which we are about to compute. And finally, the contribution from the counter terms, finite quantities of the same form as the things occurring in U, which we do not know until we fix it, which are determined in terms of the others once we fix our renormalization conditions. V scalar is 1 over 64 pi squared, trace U double prime squared, log U double prime. V fermion is minus 1 over 64 pi squared, trace m of phi, that's the fermion mass term, m of phi bar, m of phi bar adjoint. For some reason I'm putting in the explicit phi bars in some places and not in others, squared log m adjoint. We now want to compute the contribution from the gauge fields. At first glance, we get a horrible mess because we can have not only graphs of the sort we feel we can handle by our techniques, where there are scalar fields on the outside and gauge fields running around, but also the possibility of a graph in which, say, something like this happens. Because, after all, there are trilinear scalar-scalar gauge fields interactions. However, by an astute choice of gauge, we can make these disappear. I should, by the way, warn you, this is a remark I should have made earlier, as soon as we have a gauge field around, the effective potential is, of course, not a gauge invariant object, because the phi fields are not gauge invariant objects. They transform under the field theory. That is neither here nor there. It is not a gauge invariant object. Nu, it isn't a gauge invariant object. The propagator isn't gauge invariant. Nothing is gauge invariant until you put everything together and assemble physically observable quantities. Any gauge should be as good as any other gauge as long as you don't change gauges in the middle of the computation. Now, we will use Landau gauge, in which the propagator is proportional to this. Why is that a good gauge? Well, let's focus attention on what's happening at this vertex. Here a scalar meson is coming out with momentum 0. Here a photon is coming in with momentum k, or gauge meson, and here a scalar meson is going along again with the same momentum k. Therefore, the sum, or difference, depending upon how you orient things, but in this case it doesn't matter, of the momenta carried by the scalar meson is k. Therefore, we have a k mu suppressing indices, k mu times a mu, because it's always the sum of the momenta. And in Landau gauge, that hits this propagator and vanishes. Okay, is that clear to everyone? So as long as this momentum is 0, this vertex vanishes. Therefore, we don't have to worry about that, and we just have to worry about graphs of the first kind we've got here. What are those graphs? Well, we can discuss them Here's a typical one. They're graphs of this kind using a little black dot to indicate that four-meson interaction, just the same way as before. That black dot is, of course, comes from the term in the Lagrangian plus GA CABC, no, not CABC, forgive me, GA TA phi bar, the GB dot, GB TB phi bar, A mu A nu, A mu, upper mu, B. That's the d mu phi term expanded out to give us this interaction second order in A squared. This is, of course, simply the mass term of the vector meson in the presence of an external phi field. And therefore, the form of this vertex, and there's a 1/2 here, it's 1/2 d mu phi bar. Therefore, the form of this black dot vertex is simply IG A, B, the coupling, sorry, I, G mu nu, because the two indices are the same, times a quantity which we can call m squared of phi bar AB, and it's defined up here. It is the mass of the vector meson in a given phi bar field, the vector meson mass matrix. That's just like the fermion case where we have m of phi appearing at each vertex. Now we've got to worry about all those propagators running around. The propagators, thank God, are delta functions in AB space, but they do have mu nu indices. Here I've got I, delta AB, minus I, a G mu nu minus K mu K nu over K squared, over K squared minus I epsilon. Fortunately, the I up here and the minus I down here cancel off against each other. You always have one propagator for each vertex. Fortunately also, this object is a projection operator in mu nu space, and therefore whether you multiply it around 17 lines or 3 lines or 121 lines, you just get the same thing, G mu nu minus K mu K nu over K squared. And at the end, you have to take its trace. That is to say, G lambda lambda minus K lambda over K squared, which equals 3. Otherwise, the computation is exactly the same as a scalar or spinor or any other computation we've done. We've got a string of matrices running around. We have a 1 over K squared plus I epsilon for every internal line. Therefore, we can just write down the answer, and I will. The only difference is a factor of 3, coming from the trace of the Landau gauge propagator when we finally sum up all the space-time indices. See, it's not a hard computation at all. Plus 3, 64 pi squared, m squared of phi bar, trace, m squared of phi bar squared, log m squared of phi bar. Is the argument clear to everyone? All the index structure collapses and it becomes a scalar computation all over again because we're cunning in our choice of gauge. Now, note, this has a definite physical meaning, just like the others did. Remember I said this was the zero-point energy of a sum of independent harmonic oscillators. Well, so's this. Why does it have a factor of 3? Come on. Massive vector meson has 3 degrees of freedom. Massive scalar has 1. So we've got 3 times as much zero-point energy. There are 3 virtual oscillators for every momentum state of a massive vector meson. Okay? Physically clear, right? Couldn't be clearer. Any questions? These formulas will be important to us next lecture. At the moment, I've just been accumulating them, but when I finally discuss things like Weinberg's famous lower bound on the mass of the Higgs meson, which I hope to get to. I'll use these formulas. But they're very simple. I mean, you can remember, aside from the 64 pi squared, which one has to memorize, you figure out what they are just by counting up 0-point energies.
And remembering the term uniting sign for the end.
Yeah, but that's because the 0-point energy goes the other way. Instead of subtracting the 0-point energies of the individual oscillators, you're adding the energies of the negative energy state, filling up Dirac's holes. Now, that concludes that, and that concludes the general part of the discussion, at least for a while. And I'd now like to turn to the thing that makes all of this interesting, because so far this has just been, aside from our discussion of the sigma model as a model of current algebra, all the stuff about gauge fields and Higgs phenomena and so on, albeit it may have been beautiful and elegantly and wittily presented, is nevertheless just a theoretician's toy with no apparent connection with the real world. I will now discuss, or point onto a discussion, which I will complete next lecture, of the famous Weinberg-Salam. Here, neither of them got any hints from me. They did it all themselves. Weinberg-Salam model of weak interactions and E and M. This is supposed to be a model that actually describes the real world when sufficiently generalized. There are many, many variants which are properly the subject. There's the Glashow-Georgi model, there's the Patti-Salam model, there's this model and that model. This was the first one discovered and remains the simplest one. These are all models that are cooked up to give a renormalizable theory of the weak interactions. You recall when I wrote down the weak interaction Lagrangian, the current form, one of the things I said about it was that it was non-renormalizable. We couldn't compute higher order corrections. In practice, of course, that didn't matter for most experiments because the coupling constant was weak, and nature seemed to work out in such a way that even the square of the Fermi constant times infinity was a small number. It's very hard. It's very hard to find experimentally any corrections. However, it was a beau ideal of theoretical physicists for many years to somehow concoct a renormalizable weak interaction theory. And Weinberg and Salam did it. They did it by constructing a gauge field theory with spontaneous symmetry breakdown that had the properties. This theory was guaranteed to be renormalizable because it was a gauge field theory with only renormalizable interactions. Involving only small coupling constant, everything is treated perturbatively. 100% guaranteed to be renormalizable. After the dust of spontaneous symmetry breakdown settles, of course, it doesn't look at all like a gauge field theory. It's got massive vector mesons as well as massless ones. There's one massless one left that becomes identified with the photon. It's got horrible interactions. The whole thing looks grotesquely and disgustingly non-renormalizable, but that's an illusion. There, just as in our discussion of the sigma model, there are all sorts of secret relations among the coupling constants, which are preserved by renormalization because it's secretly a renormalizable, completely symmetric theory. And these secret relations guarantee that when you compute everything out, everything remains renormalizable. That's the importance of my answer to your question earlier, that renormalizability and spontaneous symmetry breakdown are separable phenomena. Now, the model, what will it have to involve? Well, it's going to be a model of spontaneous symmetry breaking that occurs in perturbation theory, so it had better involve fundamental scalars. It's going to be a model where they're going to have some hope of representing the real world, so we don't want any Goldstone bosons around at the end, because they certainly aren't there in the real world. So we'll have to involve gauge fields to eat the Goldstone bosons and become massive vector mesons. Well, the only gauge field around is the photon. The real world also has in it leptons and hadrons, possibly quarks. So it had better have leptons. And although we're not going to expect to use perturbation theory to gain much insight into strong interactions, we'll eventually have to extend the model to contain either fundamental baryons and mesons or colored quarks. The version of the model I'll discuss here, and maybe the only version I'll discuss, I haven't worked out the timing of next week yet, will be a version which has only scalars, gauge fields, and leptons. And in fact, I'll draw a line through there, since in the first version I'll discuss the only for simplicity, I'll only discuss the electron and its neutrino, and then the next lecture, or I will tell you what happens if I put in a muon and its neutrino. So it's a very simple weak interaction theory we're going to try and simulate for a trial run, one in which there's only a current-current interaction between electrons and their neutrinos, a phenomena that in fact has not been observed experimentally. Muon decay, of course, has been observed experimentally, and we will get to a theory that involves that. Now, the gauge group, the first thing to state is what is the symmetry group of the theory. There will be a gauge group that will be U2. That is to say, U1 cross SU2, SU2 plus phase transformations. This is very much like the isospin and hypercharge of the strong interactions, and therefore, so I don't have to invent a complete terminology, I'll call the generator of this one Y, and the generators of this I. They're, of course, not the real Y and the real I. They are a weak interaction version of Y and a weak interaction version of I, and indeed, since the symmetry is going to be spontaneously broken, they don't correspond to any invariances, manifest invariances of the real world. There will also be an additional U1 factor that has nothing to do with the additional symmetry, having nothing to do with gauge transformations, but which I'll just impose a condition on my possible Lagrangian. Lepton number, which will be a phase transformation on the Fermi fields. Notice that since I have a 4-parameter gauge group, I will have 4 vector mesons. One corresponding to the weak hypercharge, which I will call V mu, and 3 corresponding to the isospin generators, which I will call W mu A. A goes from 1 to 3. Since these are 2 independent groups, they have 2 independent gauge coupling constants, which I will call G prime and G, following the line curve. Okay. That completely determines, once I have stated the scalar field and Fermi field content of the theory, the interactions of the vector mesons. They're then followed by the minimal coupling principle. Now I must tell you what the scalar fields are and what the Fermi fields are. There is only going to be one multiplet of scalar fields. It will have I equals 1/2 and Y equals 1. That is to say, if this were real I and real Y, it would be the kaons. It therefore, I'll call it K. And write it as a 2-component vector. And abusing language, since at this level I don't know what electric charge is, since the symmetry hasn't broken down yet, I'll standardly call things K plus and K naught, just like the kaons. The scale, at least in the paper I copy things some, which was a set of lecture notes by Alvaro de Ruhela, because he's normally meticulous in his conventions, is somewhat unconventional, the scale of the generators, but it's defined once we write down the derivatives. And I'll write that down, the covariant derivative of K. That's, of course, the ordinary derivative of K plus IG over 2. I'm going to run 10 minutes over, I think, today, but that's okay. TA, that has to be there. W mu A K. That's the right form, TA is the ordinary Pauli isospin matrices. Now no longer real matrices, but complex Hermitian ones. C plus, and he put in a minus sign here for reasons which are obscure to me, but I'll stick with him. Minus sign of 1/2, which is also obscure, but that's all right. That just means that's just a question of how you scale a generator, and he's free to do that any way he wants to. G prime over 2 V mu K. This is the isospin part, and this is the... No, well, it works out this way. Okay, I'll just keep to this. You agree I have the freedom to do it, since in my general discussion I didn't say how I was going to scale the generators, so I could call them minus the generators or whatever. I can stick in minus signs or plus signs as I will. The d mu k bar, which is of course a column vector, if this is a row vector, is the ordinary derivative, minus ig over 2 w mu a, k bar ta, plus I g prime over 2 v mu k. K bar, thank you. The part of the Lagrangian involved, these are going to be the only scalar fields in the model. The most general Lagrangian invariant under the group, allowing at this level, stage, allowing the possibility of spontaneous symmetry breakdown, is the free gauge field part, which I will not bother to write down. That's our standard thing. Just the abelian electrodynamic thing for V mu, and the standard thing for W mu A, the triplet, plus d mu k bar dot d mu k, normalizing things so that there are complex fields. That's the gauge invariant interaction. There can't be any derivative interactions because of non-renormalizability, but we're allowed quartic and quadratic non-derivative interactions between k and k bar, no trilinear and no linear, because with 3 isospinners you can't make a scalar, and with 1 isospinner you can't make a scalar. So the only symmetric thing is minus some coupling constant lambda over 2, k bar k minus a squared squared, where I've summed things together in our conventional way, giving us 2 parameters so that there is spontaneous symmetry breakdown. Of course, it's possible to write down an invariant Lagrangian that does not display spontaneous symmetry breakdown, where this a squared term has a negative sign. But otherwise, that is the most general renormalizable Lagrangian we can build with the fields we have so far. I'm now going, the fermions are of course very important, but let's take a preliminary look at what happens here. In tree approximation, which is where we're going to investigate this model, we have the minimum value of k. K is a two-component complex vector. Therefore, that sum of the 4 squares of the real parts must be a squared. With the full U2 group at our disposal, we can take any two-component vector and make it any one of our basis vectors. Which one we choose doesn't matter. They're all connected by the symmetries. It's just a redefinition that tells us physics in any one is the same as physics in any other. In order to utilize this notational coincidence as much as possible, I will choose the symmetry breaking so that k equals 0a. Or I should say the expectation value of k equals 0a. I could have chosen it to be any unit vector. Notice it's the presence of the additional U1 group that allows this to be possible. Otherwise, well, no, I could even do that just using SU2. I take it back. I just pick it to be a basis vector. The advantage of this is that the expectation value of k does not break electric charge conservation, since it is k0 that develops an expectation value. On the other hand, the other 3 of the 4 generators of the group are broken. There is no, you can make a phase transformation along this axis and one on this axis, and that's all you can do. Therefore, we know already we expect to find one massive scalar three goldstone bosons, which are eaten by the three of the four gauge mesons to make three massive vector mesons. We also know that two of these will carry charges, plus and minus. They will be the isospin raising and lowering vector mesons, since electric charge conservation is not violated. One of them will be neutral. It will be some linear combination, which we have yet to compute, of the ice of 3 vector meson and the hypercharged meson, since there are 2 electrically neutral generators.
How are you finding the electric charge here?
The electric charge is the single remaining symmetry. This is supposed to be a realistic model, and the only massless gauge meson we know about is the photon. There will then be one massless meson which of course will be electrically neutral and will be the photon. It will be identified with the photon. As we'll see the other 3 massive mesons will end up being the intermediate bosons that simulate the exchange of which simulates the current-current interaction. But I haven't gotten to that yet because I haven't gotten to the leptons, which have their currents. But we see already on this level that we have a model which will at least meets the minimum criterion of a realistic model of the weakened electromagnetic interactions, to wit, its symmetry breakdown is such that there is only one massless vector meson remaining. Is everyone happy with that? I'm not going to complete this discussion, this lecture, even if I do run 10 minutes over time, so if you're not happy, please ask me a question and we'll just talk a little more next time. Okay. Notice this is perfectly general. The way this model is cooked up, once I have stated the symmetry transformation properties of the fields, and that the interaction has to be of renormalizable type, once spontaneous symmetry breakdown occurs, it occurs in such a way so that there is only one parameter unbroken group. There's only one massless vector meson left at the end of the game. Now, I now turn to describing the fermions. Again, it will be the same thing. I will give them transformation properties that are very strange indeed, but that's my freedom. I can say how they transform under this group any which way I want to. And then once I have stated that, I will write down the most general interaction involving them. And then I will study the effects of spontaneous symmetry breakdown on the fermions. This is a theory which knows from nothing about parity. When you first hear about spontaneous symmetry breakdown and you say, oh, that's marvelous, parity non-conservation is going to arise as a consequence of spontaneous symmetry breakdown. That's how we're going to get parity non-conservation in the weak interactions. The Weinberg-Salam model goes exactly the other way around. It says that the original dynamics which God created before spontaneous symmetry breakdown occurred is so ignorant of parity that it's not even written in terms of direct 4-component fields. It's written in terms of Weyl fields, those 2-component fields. It's not parity non-conservation in the weak interactions that's the result of dynamics. It's parity conservation in the electromagnetic interactions. That's the result of a dynamical coincidence. So, let's see how that runs. I will now state the fields and their transformation properties. I will firstly have to introduce a little notation to write left and right-handed Weyl fields. I will write them, those are, remember, 2-component objects that correspond to eigenstates of gamma 5. For convenience, so I don't have to go back to that crazy sigma notation, and I can still use gamma mu's, I'll just take a 4-component field and break it up into what I will call a left and right field. These are gamma 5 eigenstates. Note, because gamma 5 is anti-self bar, the corresponding expression for psi bar has a minus sign in it. Psi is, of course, psi left plus psi right. Psi right. And finally, if I go to a basis in which gamma 5 is block diagonal, in fact, actually diagonal, 1 minus 1, 0, 0, psi left is something, something, 0, 0, and psi right is 0, 0, something, something. So even though I have written them as 4-component spinors, they really only have 2-component objects. 2 of them are zeros by the equations that define them. A trivial computation shows that psi bar gamma mu psi is psi right bar gamma mu psi right plus psi left bar gamma mu psi left. That is to say, the free Lagrangian does not mix rights and lefts. If you only had the kinetic energy, the two helicity states would be dynamically independent, whereupon the mass term, psi bar psi, is psi right bar psi left plus psi left bar psi right. That will be useful to us in 3 minutes when we make a transcription table. I am now prepared to state the two fields we have here. Both carry lepton number. There is a doublet which is completely made up of left-handed fields and which I will call L for left-handed. It has I equals 1/2 and y equals minus 1. It's like the K-bar field that way. To write down its covariant derivative, d mu left is d mu left plus I g over 2, the same as before, tau a, w mu a left, and this term changes sign, so it goes to plus, where it was minus before.
You see a minus on the last term because d mu k bar, you have a minus I g over 2 d.
That's because it's acting on the other side. That's written as a row vector. This is written as a column vector in the isospin space. Now, there is also a right-handed field, which is just an isosinglet, and has y equals minus 2. Very funny, like the omega minus or something. Okay, but that's it. That's my rules. I'll put in any fields I want to and let the symmetry breakdown go. Now there's no 2 here. I'm sorry I'm going to run over time, but after covering the blackboard with these equations, I don't want to cover them again at the beginning of next time. Now let's give these components of these things suggestive names, because we can tell what their charges are. This is just suggestive names, because we'll know when spontaneous symmetry breakdown takes place if we choose the K field to move this way. Oh, sorry, first, no, forgive me. Let me write down in this corner the Lagrangian. There's the terms as before. There is, of course, the gauge invariant kinetic energy, defined in terms of those things. And now I can put in Yukawa couplings. Okay, that's my freedom. That's the only renormalizable interaction these scalar fields and other fields can have. Because of the way I've hooked them up, notice the hypercharge of this minus the hypercharge of this. Have I got it somewhere? Yes. Equals the hypercharge of this. So I can make a Yukawa coupling by putting together left bar and K and the singlet that conserves hypercharge. Left bar K and right. So I can have some coupling constant minus F, left bar K, right. I've chosen my hypercharges, so there is a Yukawa coupling possible. If I hadn't done that, I would have gotten a rather trivial theory, because I would have had no interactions between the fermions and the scalar mesons. Plus, of course, Hermitian conjugate. And by a proper phase choice, I can always make F positive by choosing this phase. Okay? Is everyone happy? This is the most general renormalizable interaction. Is there uniform, universal happiness about this point? You might say, couldn't I put a gamma 5 in here also? No, because these are gamma 5 eigenstates. So if I put in a gamma 5, that's just putting in a factor of 1 or minus 1. It's not an independent coupling. Those are them. Those are all there are, okay? Lots of free parameters, but we've written down every one. Now, Jesus, I'm going to run. It's going to be a long lecture. Well, it's the end of the semester. Now, let's let it run. What's going to happen? The first thing is we're going to have electric charge left as a symmetry. Therefore, we can take left and right, and we'll break them up into the first and bottom components and figure out what their electric charges are. Left. Up here, there will be a negatively charged field, like the K minus. It's got the assignments of the K minus. With malice aforethought, I will call that field left-handed electron. Down here, there will be a neutral field, like the K naught. I'll give that a name. It's my freedom to give it a name. I'll call it nu, left-handed neutrino, electron neutrino. Up here, right has only got one field, which is because of the way I've assigned the hypercharge, has charge minus 1, I sub z plus y over 2. I will call that E right. The result of spontaneous symmetry breaking on the mass terms is, of course, just reading things off from this coupling constant, the quadratic terms only. That's the first thing. We'll also to know the interactions with that scalar meson, remaining scalar meson, but that's neither here nor there. L equals dot, 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 plus, minus, excuse me, F A, which gives me the scale of the breakdown. Okay. Now I have L bar K. K has only got a lower index. So I pick up, whoops, did I do it backwards? Yes, I did it backwards. Yeah, sorry, nu left, E left. Sorry. Charge always goes up when isospin goes up. So that just picks up E left and couples it to E right. This is, of course, simply a mass term. There it is. The effect of we start out with the 3 massless Weyl fields that have absolutely nothing to do with each other. Okay, one of them is a weak doublet, one of them is a weak singlet. Miraculously, right down the most general renormalizable interaction Lagrangian, we make the shift, a mass term appears. It's a miracle. The mass of the electron is minus Fa. The neutrino remains massless. There's no way we can give the neutrino a mass. We've done the most general case, and the mass comes out to be 0. Of course, we'll always be left up with one massless particle in a theory of this kind because we start out with an odd number of Weyl fields. We can pair 2 of them together to make a mass term, but then the third one is just left there. Okay, is everyone happy? I'm feeling guilty about running severely over time. I offer you an option. Should I talk for another 5 or 10 minutes, or should I stop now and continue in the next lecture? Those who want me to continue talking. Those who want me to stop. I'll continue. I know he'll talk about Zionist influences in physics lectures. No. The Spiro-Agnew... Well, let me go on, because as we... No, it's... Okay, I'll stop here. So thank you for that modest but no doubt sincere praise. Now, let's go on and compute the mass. So far, I mean, that's nothing. We don't know F, we don't know A. That's hardly much of a relationship. But we've seen how the electron gets a mass and the neutrino doesn't. And next lecture, we'll see how the muon gets a mass and the muon neutrino doesn't, by the same automatic mechanism, no matter what the coupling constants are. Now let's go on and compute the vector meson masses. 3 of them are massless, and 2 of them are massive. I want to keep those covariant derivatives on the board, so I'll erase this for the moment. There's a term plus that's going to get the masses as a result of the shift when these k-bars are replaced by their vacuum expectation values. The d mu ordinary derivative part of the d mu will give me nothing. The other part will give me a part linear in this vector fields, which when squared will give me the 3 approximation masses. Now, there are 2 kinds of terms, obviously. There's W1 and W2, which involve tau 1 and tau 2, and turn this lower vector into an upper vector, which then gets squared. And then there are the 2 neutral ones, W3 and V mu, that turn the lower one into itself. So let's write down those 2 terms separately. There's a 1/2. W1 and W2 obviously do the same, just come in the combination. That's the square of the upper component of this vector, using these things here. And of course, there's an a squared, because it has got an a in the scale. The lower component is a bit different. Here I get G W3 plus G prime. Well, I've still got the 1/2, so I've got a squared over 4. G W mu 3 minus G prime V mu, the signs are opposite, squared. That's it. That's the vector meson mass matrix. Now let's diagonalize it. Well, it's pretty easy to diagonalize it. Part of it is diagonalized at all. W1 and W2 are equivalently W plus and minus, which is 1 plus I times the other. Let's see, it's 1/2 the mass that appears. G squared A squared over 2. In addition, there is a massive neutral meson, which I'll call Z. I've got to normalize it properly. Yes? I've got to normalize it properly, so I'll write Z is G W mu 3 minus G prime V mu over root G squared plus G prime squared. That's the normalized field. The kinetic energy has the right form. The mass squared of the Z, as we see from here, is just this thing squared times A squared over 2 times G squared plus G prime squared, which is, by the way, greater than the mass of the W plus and W minus. Finally, there's the remaining orthogonal neutral meson. Plus G V mu over the same square root. That orthogonal combination has nothing in it. That's reasonable. We have an unbroken symmetry. We've got to have a remaining gauge meson. That's the gamma. Okay? So, we have a charged doublet of unknown mass until we give the parameters of the theory, a neutral massive meson of equally unknown mass, except guaranteed to be heavier, and a massless vector meson. Now, where do the weak interactions come from? I'll just do the weak interactions now, I'll let you go and then come back and do the electromagnetic interactions next time. Here comes the cunning part. Let's look at the charged part of the current after we've made the shift. That comes just from this thing here, all right? Just from the tau a's. Those are the only charged things. So that part of the Lagrangian, I can now erase this since I'm not going to use it until next lecture. Here comes the real wonder. I have a 1/2. I always get a square root of 2, so I get minus g over root 2, that's the square root of 2. New bar left, E left, gamma mu, W mu plus Hermitian conjugate. That's the unique part coupling the charged vector mesons to the fermions. Is everyone happy with that? You happy? I just extracted it out. Okay. So, please notice, this is automatically of the 1 plus gamma 5 form. Left is 1 plus gamma 5 over 2 times the field. So the interactions are automatically maximally parity violating. Now you might say, that's nice, but the weak interaction is current times current. Let me just write that for emphasis. This is psi bar neutrino, gamma mu, 1 plus gamma 5, psi e, g over 2 root 2, because of the 1/2 in the definition of left. Now, this is automatically parity violating, and it leads to a 4 fermion interaction as a result of vector meson exchange, a plus on one end and a minus on the other. What is the vector meson propagator? It is G mu nu minus K mu K nu. It's a massive vector meson. That's what we get in U gauge. K squared minus M squared times minus I. And then there'll be an I squared from the 2 vertices. That'll turn that into a plus I. What happens to this if I imagine the meson is very massive compared to, say, the mass of the electron? So K is much less than M. Then this term is Bupkis, this term is a constant, and I simply get minus I G mu nu over M squared. Okay? That is to say, I get a point for a small momentum transfer, small compared to the mass of the vector meson. I get a point coupling, a Fermi coupling with the identification G over root 2 equals G squared from this vertex, 2 root 2 squared G squared over 8, as I've defined it, M squared. Equals, as we see here, since this is the plus or minus charged vector meson, 1 over, let's see, that's 8M squared is G squared, no G squared, 1 over 4A squared. Is everyone happy with that? Now, please notice, the weakness of the weak interactions is revealed to be a delusion. The only coupling constant in these theories are G and G prime, which, as we will see next lecture, are both on roughly the order of magnitude of the electromagnetic coupling when we extract the coupling of the photon. This has nothing, the smallness of the Fermi constant has absolutely nothing to do with the presence of weak dimensionless parameters. Simply has to do that the A parameter, a parameter with the dimensions of a mass, that entered the original Lagrangian was very large compared with the electron mass, which sets the normal scale of mass, or the muon mass, which we will get to next time. That, remember, the electron mass was Yukawa coupling constant times A. So the weak interactions are weak, not because there are weak, super weak dimensionless coupling constants around, like 10 to the minus fifth, okay? But because there's a super weak Yukawa coupling, F, that makes the Fermi mass, the fundamental fermion mass, the electron mass, much smaller than the characteristic length scale A, which is the only parameter in the theory with the dimensions of length. The weakness of the weak interactions are not due to weak couplings of these vector mesons, or due to the fact that they have large masses compared to the masses of the leptons, and that's because they have, not because the vector fields have weak dimensionless coupling constants, but because Yukawa couplings are weak. It's the weakness of the Yukawa couplings that makes the weak interactions look weaker than the electromagnetic interactions. But I've run grotesquely, unforgivably over time, and we'll talk about the electromagnetic interactions and muons and quarks next time. Please forgive me. I just got carried away.